Hey, hi. Kinetic molecular theory and ideal versus real gases. We kind of brought it up in class today, a few hours ago. So I'm just going to put it on paper, make a couple adjustments to the assumptions and how the consequences of those. Okay, so let me share my screen. Share that. I'll try to keep this short and sweet. All right. So first off, we'll look at that equation in a minute. All right. We'll look at that momentarily. Kinetic molecular theory, right? I'm just going to tell you some key points and why they're important. KMT. All right. Gas particles have negligible volume. So we assume that the particles themselves do not take up space, and therefore the size or the negligible. Therefore, the volume of the container is the volume that the gas particles have to roam, negligible, right? If that doesn't make sense to you, think about, if we were all stuck in a room and wanted to walk around, we would have to subtract the space that all the people take up in order to figure out how much space we actually have to move around. Because compared to the amount of space that we have in a room, we actually have quite a volume that is comparable to that. Gases have a volume that's so small comparable to the amount of space that they have typically, that we just don't assume, we don't even account for the space that they take up. We also say that gas particles have no IMFs, right? So, shoot, my daughter. One gas particle is not attracted nor repelled by another gas particle. There's no forces of attractions or repulsions that are recurring. Collisions are elastic. All right, meaning that when they combine, gas particles randomly just hit each other and they move in straight motion. If they are combining with 50 joules of energy, when they hit, then they go away with 50 joules of energy. None of that is lost in that process. It's just an assumption, okay? So let's go ahead and look at where we'll see this brought up, and that will be in terms of our real, actually, let's start with ideal. Our ideal gases. Guys, ideal gases, that means they obey the ideal gas law, okay? It means we can predict these, the value of the constants and variables by using the ideal gas law. And real gases do not obey the ideal gas law. Their pressure is messed up and their volume is messed up, okay? Ideal gases gases tend to be ideal when think about it, they want to move around, they want to have low pressures so they can spread out, and they want to have high temperatures so that they don't come together. Okay, that's when ideal gases are ideal. If those conditions are non-ideal, well, they would be opposite. We would have high pressures, and we would have, in addition to that, we would see low temperatures. All right, so once again, ideal gases obey the ideal gas law. All right, and real gases do not obey the ideal gas law. And this is the case under conditions that are not so ideal for gases. And those are the high pressures and the low temperatures. Now, we should know that the ideal gas law is PV equals nRT, okay? Oops, let me get that up there. I think you can see it. Now, what I have written on my screen is a different version of that. This is getting on my nerves. I don't guess you can see that. Okay. You have a different version, or what we see is a different version. This right here is called our van der Waals equation. Van der Waals is another word for intermolecular forces. Van der Waals forces. Van der Waals equation, okay? I'm going to erase this so that I don't have to rewrite it over. You probably just wrote it further down on your paper, I imagine. Okay, so what we see here is our, well, I'm not going to go through it until I explain it to you because that would make more sense. But this is the equation for real gases. Okay, you're not going to have to use this equation, but what we need to be able to do is identify what A is and the idea behind it, and we need to be able to identify what B is and the idea behind it. So that's what I'm going to attempt to tell you right now, and then we'll be finished with this little idea. Okay, I don't want green. So let's go back to our real gases and let's break this down. When the pressures are high, high pressures denote, if you will, entail, relate to, correspond with low volumes, right? And as the volume gets smaller, the smaller the volume, maybe you know where I'm going, the smaller the volume, the less negligible the volume, the actual volume of the particles, gaseous particles is, if that makes sense, right? So if I could look at it like this, if I have a large space and a few gas particles, the space taken up by the gas particles doesn't really matter. But if I have a very small space, and that space is going to get small by increasing the pressure, okay? So it's pressure to volume to space. And if I put those particles in here, well, you see that the volume of particles is no longer negligible. And so our assumption is no longer valid. Our assumption that gas particles don't take up any space. Okay, because the volume here is no longer negligible. And here we are saying that the volume of the particle is negligible. Okay, if you don't understand, you just need to ask me and I'll try to explain it, but it's gonna be very similar. But I can give you a different example. Okay, now I'm gonna leave that down there. Those are notes I was looking at, but I like to write my own notes as I go. Okay, so if that's the case, let me go ahead and erase this because we're gonna need that space there. If that is the case, then what we have is, let's think about it. This is the deal. The actual volume of the real gas, right, is higher than what would be predicted. Because we have to add the size of the particles to it. That's the way I think about it. Now let's go up and look at our Van der Waals equation. And let's highlight this. The actual volume of the real gas is higher than what would be predicted for an ideal gas. Okay, so because they're taking up space in such a small environment, small volume already, their particles do take up space. And that's caused by the high pressure resulting in a low volume, okay? And we have made a volume correction here. Right? This is the volume correction. So B is a constant for given different, it's a constant, but it's based on the type of gas that you're dealing with, whether it's nitrogen, oxygen, hydrogen. And it is a value, a constant value for different gases. And this accounts for that volume correction, because remember, our volume would have been too high, so we're taking some away from it. All right. Okay. Now, in terms of our low temperatures, let me get rid of this. Okay. Now, okay. Low temperatures. Well, what happens is two things. Particles start slowing down. All right. And these collisions, sorry, I was just curious what I wrote down there. Particles start slowing down. So this is the way I see it in my head. And condensing, right? Because that's what happens when things cool down, and condensing. This allows for forces of attraction, which are intermolecular forces. So let's write intermolecular forces of attraction to start occurring, right? So the other assumption is no longer true, right? It's no longer true that there are no intermolecular forces. Okay, so, and we also have, well, no, let's relate that to this. And this could lead to collisions with the side of the container that have less force. And in my head, that's because the collisions are no longer, see, if I write it, y'all are going to say it, every single one. I'm not even going to write it. I'm not even going to write it. Right. So the IMFs, as we come together, we start condensing. And then when we go back apart, we're kind of attracted to each other now. So those collisions are no longer quite as elastic as they were, but it's because of the IMFs. So I don't want you to remove that from your statement or an answer and only say, well, collisions are no longer elastic. It's because the assumption that there are no intermolecular forces is no longer valid, okay? That is part, it's got to be a part of that answer. It's all about the intermolecular forces, all right? With less force, and this is because we now have forces of attraction between them. So what we see is the pressure is less than we would have expected it to be. Okay, so we have a volume that's higher, and we have a pressure that's lower. So when we look at our van der Waals equation, okay, what we see is the correction for pressure here. We see that they've added to it to bring it back up to where we would expect it to be, and if it was ideal. All right, now, if you understand what I've just said, that's fine. That's all you need to understand. That's it, right? A is dependent on the type of gas as well. It's a constant. You need to realize that this is your correction factor here, and it corrects for the pressure that will be too low. The pressure is too low because the temperature was so low. We had forces, the intermolecular force, the assumption that there were no intermolecular forces was no longer valid. So temperature gets really low, gas particles start condensing, we experience some actual contractions. They don't pound on the walls with as much pressure as they did. Our pressure is actually lower than we would expect it to be. Here's your correction factor for that. Okay. Pressure is too high. Volume goes down. Now the volume is so small that the gas particles themselves, their volume is no longer negligible. So we see the actual volume be a little higher than would have been for the ideal gas law. So we have a correction factor for that here, which lowers it back down. That's it. I probably should have just said that. Okay, I'm gonna leave it there. All right, guys. You guys are awesome. Stop share. Bye.